Hi, this is Siasi Young doing problem 18.10 from chapter 18, Aqueous Solutions with a concentration on titrations and pH. The question tells us that a 25.0 milliliter sample of 0.125 molar pyridine is titrated with 0.100 molar HCl. Calculate the pH at each volume of added acid. Volume A, 10 milliliters, volume B, the equivalence point, and volume C, 50 milliliters. What do we know? Well, we know that pyridine, our weak base, is our analyte, which means that it is in the flask. We know that its volume is 0.0250 liters. We know that the concentration of C5H5N is 0.125 molar. Hydrochloric acid is our titrant, which means that it's in the burette. We know that the concentration of HCl is 0.100 molar, and that our balance equation is HCl aqueous plus C5H5N aqueous turns into the conjugate acid of our weak base C5H5NH plus. Now, how will we find the pH of each volume of added acid? Well, first, we'll need to calculate the initial amount of our analyte, C5H5N, in moles, as well as the amount of HCl added at each volume given. Next, we'll create a mole table based on the neutralization reaction to calculate the amount of titrant, HCl, analyte, C5H5N, and product, C5H5NH+, before and after the addition of the acid. Next, we'll find the molarity using the amount of moles left over after the addition of the acid divided by total volume. Then we'll calculate the Ka using the Kb with the relationship between Ka, Kb, and Kw, which is the equation there. We'll use the Henderson-Hasselbalch equation in problem A, pH equals pKa plus log of the concentration of base divided by the concentration of acid. And later, we'll use the pH equation, pH equals negative log of the concentration of acid. Part A asks us to calculate the pH at 10 milliliters. Well, I like to convert the milliliters into liters because molarity is basically mole over liters. And when I'm finding the stoichiometric relationship, it helps to cancel the liters so that I know how many moles of each substance I have. So with step one, calculating the initial amount of our analyte, we have 0.0250 liters times 0.125 moles per liter, which is its molarity, equals 0.003125 moles of C5H5N. Next, to find the moles of hydrochloric acid, we have 0.0100 liters, which is 10 milliliters converted to liters, times 0.100 moles per liter. HCl equals 0.00100 moles of HCl. Our step two is to create a mole table based on the neutralization reaction. So we know that before the addition of the acid, we had 0.003125 moles of C5H5N. We didn't have the conjugate acid as of yet, and we did not have any amount of the acid itself. After the addition, we know that it interacted with C5H5N to neutralize the solution, which means that all of hydrochloric acid was consumed. And our new amount for C5H5N is 0.002125 moles. We also now have 0.00100 moles of C5H5NH plus. Now that we know how many moles we have left over after the addition of acid, now we will find the concentration of both the weak base and its conjugate acid, which consists of us using the moles left over divided by total volume, which is the volume of the hydrochloric acid as well as the original volume of pyridine. which give us 0.0607 molar. We do the same with the conjugate acid, C5H5NH plus. We take the amount of moles left over, divided by total volume, and we get 0.0286 molar. Now, we know that our Kb of C5H5N is 1.71 times 10 to the negative 9. We also know that Kw, which is the ionization of water, is 1.0 times 10 to the negative 14. The equation itself is Kb times Ka gives us Kw. Now we don't have Ka, but we do have Kb and Kw. And so we rearrange the equation to Ka equals Kw over Kb, which gives us 5.9 times 10 to the negative 6. We're going to use the Henderson-Hasselbalch equation. pH equals pKa plus log of the concentration of base divided by the concentration of acid. pH equals negative log of Ka, which is pKa, plus log of 0.0607 molar divided by 0.0286 molar, which gives us a pH of 5.560. Now we have three decimal places after, we have three decimal spots after the decimal because our concentrations have three sig figs. And so the three sig figs show up in the pH after the decimal place. Part B, calculate the pH at the equivalence point. We know that the equivalence point is when moles of analyte equal moles of titrant. So we have the initial or original amount of moles of C5H5N, which is 0.003125 moles. In order for us to be at the equivalence point, we must also have 0.003125 moles of hydrochloric acid. I multiply that by the the molarity of the acid, and it tells me that at the equivalence point, we need 0.03125 liters of hydrochloric acid. So the hydrochloric acid and pyridine will come together to neutralize the equation, equaling zero, both. However, the amount of our conjugate acid, C5H5NH plus, goes up to 0.003125 moles. To get the molarity, we divide it by total liters or total volume, which is 0.03125 plus 0.0250, which gives us 0.0556 molar. And then we move to our rice table, which we use because the conjugate acid is weak. It's a weak acid from a weak base, and it doesn't fully dissociate. So here we are, the initial 0.0556. Water doesn't count because it's a pure liquid, which means that we do not engage it with our Ka, Kp, KSP, Kb equations. And we have 0 C5H5N and we have 0 H3O plus. The change is minus X for the conjugate acid plus X for what are now our products. And the equilibrium will be 0.0556 minus X. And for pyridine and our acid, it would just be X. We're looking for the pH. So the equation that we're going to use to find X, or to find X, which also equals the concentration of acid, we use Ka equals the concentration of pyridine times the concentration of acid divided by the concentration of the conjugate acid, C5H5NH plus. We know that Ka is 5.9 times 10 to the minus 6 because of the equation, because of when we found Ka, which equals x squared over 0.0556 minus x. We're going to make the assumption that x is small because the concentration is more than Ka. So with that assumption, we have 5.9 times 10 to the minus 6 equals x squared divided by 0.0556, which gives us 5.7 times 10 to the minus 4. X, which also equals the concentration of acid, is 5.7 times 10 to the negative 4. We know that our pH equation is pH equals negative log times the concentration or of the concentration of acid, which equals pH equals negative log 5.7 times 10 to the minus 4, which gives us a pH of 3.24. The pH at the equivalence point is acidic, which was expected with a weak base as the analyte and a strong acid as the titrant. Now to part C, where we calculate the pH at 50 milliliters. Again, we have the initial concentration of pyridine, which is 0.003125 moles, and we convert 50 milliliters to liters, multiply it by the molarity of hydrochloric acid, and we get 0.00500 moles of hydrochloric acid. We create our famous mole table and see that with the addition of the hydrochloric acid, there's more hydrochloric acid than there is moles of pyridine, which means that pyridine becomes our less substance. It becomes the substance that we have the least of. It works together to attempt a neutralization, but the hydrochloric acid, because it is in excess, consumes all of the pyridine and has 0.00188 moles left. Our conjugate acid, C5H5NH plus, as a result, has 0.003125 moles after the addition of the acid. Now, we know that we need the concentration of acid in order to find the pH. So we divide 0.003125 by total volume, which is 0.0750 liters, which gives us 0.0251 molar. pH equals negative log times the concentration of the acid, which is 0.0251, which gives us a pH of 1.601, which is extremely acidic. It's very acidic. And again, that makes sense because we had a strong acid with a weak base. And at this point, we are past the equivalence point. We are now at a place where there's excess hydrochloric acid, and we've completely depleted the amount of pyridine. For our summary, I'll go over the solutions for each volume of added acid and the steps taken. So we identified the stoichiometric ratio. We calculated the initial amount of analyte in moles. We calculated the titrant at each volume added in moles. We found the Ka from the Kb, created a mole table, calculated the concentration of analyte and product by dividing the amount of moles by the total volume. We either use the concentration of acid and base to calculate the pH using the Henderson-Hasselbalch equation, or we use the concentration of H3O plus after the addition of the acid and calculated the pH with pH equals negative log times the concentration of acid. Remember that the pH will have the same number of sig figs in the concentration after the decimal place. Our solutions for volume A, pH equals 5.560. Our pH for volume B is 3.244. And our pH for volume C gave us 1.601. Thank you for watching.